Swayam Prabha. Digital India. Educated India.
First, I want to remind you what we learned in previous 3 hours lecture, and then say what we are going to teach today. And we talk about alternating water column, right? Then the air in and out drive the turbine, okay? And this can be very useful, especially for the land-based or floating-based can be there. And many of the European wave energy converter or in operation are based on this principle. And we also learned particle off, right? We talk about linear electromagnetic transducer and motion transmission plus some generator, right? We also learned piezoelectric, triboelectric, such kind of energy converter for small scale energy. And for us, usually we use larger scale, therefore electromagnetic is used for. Direct drive electromagnetic transducer like that usually is very, very heavy, right? Most likely we are going to use motion transmission. This motion transmission can be mechanical motion transmission, can be fluid motion transmission, right? We check valve like that, okay. And as I mentioned, that motion transmission is very important to design. It will have influence to the dynamics, to the efficiency of our system. Simply, right, without any considering of friction, you say it will have damping effect, it will have mass effect, it can have stiffness effect, right? And such kind of transmission, you can take a look at this class, Fundamental of Design, offered by Professor Alex Slocum at MIT. He put all the courseware online on YouTube. You learn how to design the motion transmission system, okay, fundamental design. So, as I mentioned, that wave energy is really multidisciplinary research, and this course is designed originally for the precision machine system, but you can learn and use for the wave energy. And we also talk about power electronics, right? Power electronics, I highlight the importance of power electronics for the impedance matching, right? Beyond voltage, voltage regulation and voltage both up, right? So then today we are going to talk about wave energy control and also control co-design concept. And after that, I'm going to talk about society engaged research convergence for island and coastal community. And I want to get across one idea. It's like that. Even we talk about control co-design, that is the engineering framework. And when we develop wave energy converter, it's beyond engineering. This is why I talk about society engaged or community-centered co-design. Okay, that way drive research convergence. So let us start here. And wave energy control and control co-design. So here we talk about hydrodynamics control, PTO control, and briefly recall power electronics control, then talk about control co-design. So this gives you a sense, right? So no matter buoy and flap, this type of surge wave converter and alternating water column, the energy transmitted from wave energy, right? You remember what's wave energy? Wave energy, the power transferred by group wave speed, and that is proportional to amplitude, right? Amplitude square, right? This wave energy get converted into mechanical energy through buoy, through flap, through aerodynamics like that, right? Then such kind of generator motion will transmit that into electricity. Then you have power electronics to regulate the voltage and to control the impedance. And not only this control, and you have hydrodynamics are important, right? The capture with ratio, how much energy get converted mechanical energy is this important concept. Here you have motion control, you have impedance control. So as you can imagine that way, when we talk about control, it includes hydrodynamics control and this motion control, impedance control in power electronics, right? As I said, and today, second half, we are going to talk about community, society, environment, the type of thing for the design side. So, and recall that capture with ratio is mechanical energy and wave energy, right? So totally wave to wear efficiency it include capture with ratio and also PTO's efficiency. For the certain we build, right, capture with ratio get 50-60%, and PTO efficiency get 50-80%. Okay, keep in mind this is best so far, and this in a large range. For example, PTO efficiency, you drive at a smaller wheel, and the efficiency can be very small, right? And the design is very important to make sure that the maximum efficiency of the two happen at the same condition, right? In that way, you have better power output. Okay, so this is more like this time together, and here, as you can see, such kind of capture with ratio different structure, like two body system, you have 50, about 60%, and the reference model, and it's 28%, single body, and 40%. And this depends on wave input, right? Here for wave flux is scaled model is 7.5 watts per meter, corresponding to full scale about 60 kilowatts, right? So if the input condition change, the efficiency change. Okay, so and this capture with ratio. Okay, and overall, like this system, we get a 20% of efficiency. As you can see, the power output and power and history and square root power corresponding to the voltage. Here we use constant resistor. So the peak to average ratio is about 15 if you consider the rho mean square of voltage is 4 times, right? So, and this is 15 drive our design tool because our PTO and all the motion transmission and power generator and also power electronics, we need to handle the worst case, the big power, right? Where we produce average like this. Okay, so now how to achieve best efficiency, we need to consider all this, right? And control can play important role. And this one I take from this reference and paper. Okay, variable geometry wave energy converter design. So it's written by a paper Nathan Tom in Unreal, and he provides this figure. Okay, so as you know, you have wave amplitude, right? The wave is really small, and like wind energy, very small. You have cut off speed. Below that, you don't generate energy, right? Like if wind energy is too large, wind speed is too large, you knock down the wind turbine, you don't generate electricity. Wave follow similar same, right? So at small wave speed, you don't generate energy, and if wave amplitude is above a certain number, okay, then you share the load and make it flat, right? Then you have cut off, you just knock things down. This region is important, and for certain area, for example, recently I traveled to Taiwan, and the collaborator said, okay, in Taiwan we need energy in the summer, because summer they need air conditioning, and where wave energy is very small in summer, very large in the winter, right? So, and they don't want to say, okay, cut in this one, we want more to left side as much as possible, so that at the small wave speed we can generate energy. What we can do? Okay, so that is one concept Nathan Tam at NREA proposed. Okay, you can say this alternating wave surge device, and at a small wave, and the have like these windows are all closed. In that way, you have large excitation force. Therefore, you push this curve power to the left side. It can work well at a small wave condition. Okay, and then if wave is too large, then they open all the window, right? When they open all the window, reduce the power. So that is control in our geometry side. Okay, so they also did an experiment and published this paper together with Chris at the University of Massachusetts. Okay, so and you can read more about such kind of design and with variable or controllable shape or geometry. And this is for wave surge device. And similarly, Nathan Tam also proposed this design. So this is a buoy, okay, and this is still water line. You see this line, okay, and if this buoy and cross section like this one, so you pump air in, okay, then float this up, right? When you float up, okay, here you pump this tube, pump water in, make it heavier, okay. So basically, you can say that floater, you can change the geometry, especially water line. Water line, what's that water line? You remember? Stiffness, right? Hydrostatic stiffness. So you have water line like that, you have increase large area, then you have high larger stiffness, right? Or you deflate, then you have smaller. Okay, once you deflate, you have smaller surface area, water line area, okay, then you have smaller stiffness. And here you pump water inside, you can change the mass of the second system. So more details you can find in this report. I want to highlight control. Don't only think, well, where's our control, right? We can control the geometry, right? And we also can control the generator. Okay, so some other design you can control the transmission. For example, you can use variable speed transmission. Like when you ride a bike, mountain bike, you have different speed, right? Here you can design a transmission system. Yeah, at a small wave speed, you use larger gear ratio. In that way, you put generator similar rotation speed, right? That such kind of control, usually it is not that real time. What I mean, you cannot control the system this second and next second, right? You control probably today and tomorrow, depending on wave speed and also wave amplitude and like that. Okay, this is controllable geometry. And overall, what we want to show, as I mentioned, that they called SOE in terms of donors per kilowatts. This is a very important concept I want to highlight. Okay, so overall system, you want to achieve low levelized cost of energy, SOE, right? So you want to pay less donors for per kilowatt hours. How SOE is calculated? There's here. First, one by one, let I explain. Okay, and the capital expense, it including the manufacturing cost and deployment cost, and then it normalized into the annual, right? And they called fixed charge rate. So you just imagine that way. You design the wave energy converter for them each year. What kind of cost? So that is fixed charge rate. So overall is capital cost. Second part, operation and maintenance cost. This including normal operation and maintenance, and also include environment compliance cost, right? So the numerator side in terms of donors. Denominator is annual energy production. So annual energy production, IEP, that is your power rate, right? And the time the unit convert into annual 365 days, right? Another capacity factor. For example, you rated this 100 kilowatts, but this system is not always generate 100 kilowatts, right? And someday you have some days off. This capacity factor. Capacity factor can be 30–50% typically, like this range. Okay, so overall you want to reduce donors per kilowatt hours. Here, this control can play a significant role. Okay, so some research already shows, and you don't change the structure, you just use the control, you can reduce the RSOE by half. Let us say how. And so here, one thing is you can reduce the peak to average power ratio. I already showed that the peak to average power ratio in simple passive resistor case, we get 15. This is very large. 100 kilowatts device you design need to 100 peak power 1.5, right? So, and now you can use the control to reduce the peak to average ratio, right? So since all the structures, all the power electronics you designed for the maximum load, you don't design for the average, right? So if you can reduce the peak, then you can reduce the cost. And also, if you can use control, you can increase the power output kilowatts hour, right? So, and also, so in that way, and you can reduce the RSOE. Okay, I take this slides from Professor John Renwood's gas lecture at Michigan. So here he showed two papers they study, and you can show different control. And so the black line, like this, you can have constant resistor control, right? Then here it shows MPC, model predictor control. Here average, you can say you can increase the power output. Here you also compare with latching control and RQ control, right? So this is another paper shows the time domain. Okay, and you have damping, optimal damping, right? Here you have different control, what kind of performance you can have. So overall, this shows that you just use control, you can achieve more power output, right? Here in addition more power output, you can reduce the peak load too. So let us say the control concept. Okay, so you have buoy here, right? You have free surface, then you have PTO. And PTO here you assume that PTO force, and here there's PTO velocity, right? So the dynamic system is Newton's law. This is excitation force. This is radiation force, actually including added mass effect, radiation damping effect. All these are frequency dependent. Here, instead of using omega, they write S. S equal omega, this Laplace transform, right? So then you have hydrostatic stiffness, you have PTO force, right? Hydrostatic stiffness depend on water line, the cross-section area, right? So you want to increase the power here. This is mechanical power, actually. Later you will show this power into the system, right? PTO force and velocity. And later, when we say consider generator side, you will say the power you really care about that is voltage time current, this electricity. Now, let us, for the first step, let us consider this PTO force time the velocity first. Okay, so what's the control problem? The control problem, you want to have more power output here in this PTO, this power, okay, mechanical power output. That is PTO force time velocity. And now you do the integration, right? And this look like that. You want to maximum the power output and subject to velocity constraint, displacement constraint, PTO force constraint. So, and why is it different from normal one? And so, how many guys learned RQ control, linear quadratic control? No. If you look into linear quadratic control, the people care about the x square and u square. This is RQ term, and they normally don't care about cross diagonal term. Here, the control, wave energy control, the cross diagonal term is more important. Okay, so let us say, last several lectures, I highlighted for the regular wave at single frequency, right? What's the condition to maximum power here? You match the frequency, you make spring force and the inertial force cancelled. This is one condition. That is resonance condition, right? And you match the PTO damping. PTO damping is energy conversion induced damping match the radiation damping, right? You have maximum power output. Let us say such kind of system from control perspective to say what that. So, and we talk about impedance, right? So, and you have this is dynamics equation here, right? From this dynamic equation, you write in frequency domain. Frequency domain, that is your mass, physical mass. This is your added mass, right? And mass time acceleration will be the force, right? This s time velocity, this acceleration, right? So velocity dv dt, this is force. Okay, now you have excitation force, then damping force, time velocity, right? Stiffness, time, integration of velocity, displacement, 1 over s is the integration, right? You have PTO force. So you have velocity here. Now velocity impedance is defined, okay, as force divided by velocity. Now you take this 1 over impedance, this is usually called admittance. So velocity divided by this excitation force, this PTO force, this 1 over gs. gs is force divided by velocity. We call this admittance. So what's gs look like? And you already have expression here, right? And you lump them together, you will find gs itself is damping coefficient, right? And stiff mass and time j omega, right? That is what we call, when we previous lecture we have j omega is j omega time mass, right? K divided by j omega. The two force we say cancellation is here. Okay, so that is in Laplace domain. You write j omega as s, right? So that is s time mass. That is stiffness time, and divided by s. So that is there's one typo here, and what's the typo? Because Vs is already here, this is 1. Because this directly come from here, right? You take s or force divided by velocity, divide by velocity, velocity disappear. This is velocity disappear, this velocity disappear, right? Make sense? Okay, and if there's some typo, correct that. Okay, so okay, now if you want to do the control or zoom, you can measure the velocity. You want to control the PTO force, right? So basically, this is your measured velocity, and this controller you need to develop. You want to control the PTO force, right? So that system is when let me say that way. This one. Okay, so I push this first, click this first. Okay, so now this is wave energy, GS, force, and velocity, right? That is your impedance. You measure velocity, you control the PTO force, right? And the PTO force and the excitation force totally add to the control system. Okay, so now, as I said, you assume you have velocity feedback, you control the PTO force. So that is control. Okay, now the closed loop system, you have closed loop, give this PTO force input, and that is Vs equal F excitation divide G plus Cs, right? This is a control system. Okay, so you guys learned this control or no? Raise hand. This type of control? No? Mechanical engineer, you guys should learn control. Laplace transform you guys learned. Yes? So that is open loop GS, force time velocity, and you measure the velocity, you generate force, right? And this force minus this excitation force here, this minus that, then you create this closed loop, right? Closed loop system, and after you close the loop, output and excitation force Gs plus Cs, right? Similarly here, you get the power output and force time velocity, right? And you get this condition, force time velocity. To maximum power, you take complex conjugate. So what the complex conjugate mean is exactly this meaning. Okay, so complex conjugate, you have A plus BGI, right? Then complex conjugate I minus BGI, right? And you have transfer function HJ omega, H negative J omega, right? This is complex conjugate. And transmission HS, H negative S. Okay, so, and what does that mean? Okay, and just imagine the damping in impedance, the real part is damping, right? So the damping output you match, right? And then the imaginary part you get negative BJ become negative BJ, and physical meaning is you match the frequency, you match the damping. Okay, so this is control perspective about the wave energy converter. Now you given this control feedback loop, right? You measure velocity, control the PTO force, and get this, add them together. This is just this equation, right? And now GS is causal. GS means you give velocity, you have force input to the velocity output, right? You want to have self-conjugate control and complex conjugate. Okay, so this complex conjugate is not a causal system. For not a causal system, you want to design a causal transfer function here so that all approximate one particular transfer function. Okay, if you have one frequency, you match the frequency really straightforward, right? Now you have broad frequency, you want to match all the frequencies, so that is more complicated. So you need to design your the approximation quarter function, right, controller, so that you can tune based on the which frequency dominate. That is called ICC control, or approximate complex conjugate control structure, right? And I have to give acknowledge to Professor John Renwood in Ireland, okay? And another is tracking control and approximate velocity tracking. What does that mean? Okay, so instead of design the controller, right, measure velocity and control the force, and you do that way. You don't do the force control, you do velocity control, right? Now you estimate the excitation force, and use this relationship, you calculate the ideal velocity of the buoy, right? You control the buoy, let it move at the ideal velocity. That is reference velocity, right? Now you can control your system to track the velocity. So that is the ideal velocity. You measure the velocity, right? And you design the velocity tracker. Instead of design the force control, you design the velocity tracker. This is IVT control. So, and wave energy control, there are a lot of challenges, right? So, and it's like that. Almost all the vibration system, no matter what, you want to reduce the vibration, right? Here, and wave energy, when you control that, you want to increase the motion, so that you get more power, right? Instead of reduce the motion. Or the hydrodynamics part, we said, okay, linear wave theory is how beautiful it is, right? Linear wave theory assumes small amplitude, right? And here, a lot of things are not that small, right? So anyway, and that gives you sense when you implement the control, the wave amplitude increase, right? And is different from typically control system, right? Another thing is there's a force you cannot really measure, right? This such kind of the buoy, not the flap, the come here, you can measure them, the velocity, you can measure the wave, but you cannot measure the force. However, calculate from wave to the force is not causal. You remember, right? The buoy here, you want to have force. Actually, the force start before wave come to the system is not causal. So this cause problem. So, and here I highlighted hydrodynamics control. You change the shape, right? I also mentioned the PTO control, right? Where you can control the velocity, control the force in real time. Okay, so what does it mean of control force? You have generator, you control the force. In electrical, in mechanical domain, you put the force sensor. Yeah, I check the force. And in electrical domain, what you will do? What you will do? You have motor control force. You keep in mind it generates the force proportional to the current, right? Control force can also means you control the current goes through the generator. Okay, so now that is the motor generator current control, right? And you can have shape control, right? You also can control the dynamic rotation inertia, right? And different control way. And we talk about power electronics, right? And you have the wave generator. This is controlled step down converter, step up converter, both buck converter, right? Here you use duty cycle to control the switch, and this switch, right? You control when the switch on and switch off, and you can have charge discharge this inductor. And when you discharge inductor, consider that you calculate the input current and input velocity relationship. There's input impedance, right? Such kind of input impedance can be controlled using electric domain. Okay, so power electronic side. So here I want to say, recall about the core design concept. core design concept, and I give you this example what we learned, right? Mechanic motion rectifier. Okay, so this part, right? We say, okay, this move up and down, we convert the bi-direction motion into single direction rotation. It's very exciting innovation, right? You just, no matter we move up and down, my generator is always one direction, right? So you design the buoy and your teammate design the PTO. You add another teammate say, hey, your job is to do the control. What happens after that? You three guys, okay. Just imagine that you design the buoy, it's easy. Okay, you design the shape, look into hydrodynamics part, right? And then another person, okay, I design the PTO. Now give another guy to do the control. What he can do? He found out, wow, I cannot control that. Sometimes your stiffness is too high, I need to cancel the stiffness. Cancel stiffness means I need to give energy to the buoy, right? You generate the force and is negative to the velocity, right? This system, generator or motor cannot draw back side. Similarly, your pedal, and in this type of case, is loss control. That's called controllability, right? You lose controllability, then you can do nothing, right? It's innovation, exciting, but failed. So that means we need to consider the things together. You three, PTO designer, and the shape hydrodynamics guy, and another guy who's the controller, discuss together, right? You cannot say I come up very, very exciting. From my perspective, it's great, but now others are hard, right? So that is control core design, and you can think that way. One example, like you book the flight, travel to US, right? And you cannot say now where you stop by from one air flight, right? You can say first segment, second segment, right? Now you want to minimize the cost, right? You cannot say I minimize my first segment, then you will find, wow, second segment is very expensive. Make sense? You need to consider overall trajectory, then you minimize the cost. Similarly, say wheel structure and PTO side control, we need to consider them together, right? It's more like optimization iteration from the beginning. You cannot say, okay, PTO guy, you design the system and give this to controller, control engineer to handle that. This is a control core design concept. It's all about engineering system level design and iteration. Okay, so, and I give you one example about control core design. Actually, that is more details you can find. You can say this paper, one paper is by George, another is our collaboration and together with George too, and in Indiana National Lab. Okay, and control core design concept is like that. You have wheel excitation, for example, to the buoy. You have PTO and convert it into useful power. In this, you have to consider all kind of efficiency loss, right? And then I will explain a little bit more about these two terminals, right? You have excitation force, you have input impedance, right? And then you eventually, using the generator, you generate voltage, and you shunt the load, you get current, right? So let us say in a system like that one, flap, right? Then flap, I show you the flap rotate, then draw a generator. And the generator, the system, there's mechanic damping, and you can have mechanic stiffness, you can have damping. You draw generator. Generator here, you generate a voltage. However, you have generator internal impedance. And let us say one by one. So first part, I already tell you impedance, right? Impedance relationship, is force and velocity, or torque and rotation velocity relationship, right? So that is impedance Zi, right? And basically we already told you force velocity relationship, okay? And impedance Z time omega velocity here equal the PTO torque and the difference of PTO torque and excitation torque. So, and this is flap impedance like that. And second part is PTO's efficiency, impedance. And PTO is powertrain system, right? You may have the rotation inertia, right? You will have mechanical damping in the ball screw, right, system. You can have PTO stiffness, right? That is impedance of the PTO side, right? Again, you just imagine that way. Ball screw you have rotation inertia, right? Ball screw system you have damping. You may have port spring in parallel with ball screw, that is stiffness. And now your ball screw you have transmission ratio, that's N, right? And for example, if you have gear ratio 10, rotation inertia get increased by 100 times, right? So it's not surprising you have N square here. And so another thing is generator side, right? You have rotation speed, then you draw the generator form of voltage. And when you have this voltage, you use this generator power electric load, you will have internal resistance and inductance. Here, this is generator's impedance. Okay, so now you need to shunt this resistor, or shunt that you design the power electronics, right, to charge the battery or connect to the grid. It is to this system that is electric load. You need to design the controller to achieve ideal electric load. Okay, the PTO control core design system, what does that mean? Okay, you need a certain level thinking to think, okay, how to design the system with considering the flap rotation inertia, added mass, hydrostatic stiffness, or here. You need to consider your ball screws rotation inertia, ball screw damping, and PTO stiffness here. You need to consider the generator's internal resistance and inductance, right? You need to consider the generator's coefficients, torque constant and voltage constant. Torque constant, you give current, you generate torque. Voltage constant, that means you have rotation speed, generate voltage. You need to consider all this, right? Eventually, your maximum power output is achieved by looking into the voltage and current. That's the electricity you care about that, right? And a lot of time we said, okay, torque and time rotation speed, and about PTO torque, time rotation speed, that is mechanic power. Mechanic power, force, time velocity. Electric power, voltage, time current. Which one you want to maximize? Definitely you want to have more electricity. And then mechanic power is something in between, right? Previously, we always say, okay, now you match the frequency, then stiffness and inertia cancelled. Then you have force and velocity when in phase. In that way, no matter what you do, you always maximize the power, right? I give you an example, the swing set, right? You push that in velocity, then you have this swing higher and higher. That makes sense, right? You have ideal system, you have more mechanical power, then you will have more electrical power. However, and for this wave energy converter, if you consider the non-ideal case, generators, inductance, and resistance, and PTO systems damping right? And friction, all the type of things. You maximum mechanical, you maximize the mechanical power is less an idea. You want to maximize the power output. Okay, so that is the PTO control. Now, same figure you just draw here. That is torque, time rotation speed, or force, time velocity. That's mechanical power, right? Electric power is here, voltage current. And Thevenin's impedance, it means, okay, for any resource system like that, right? You look into that, there's impedance here, right? This voltage, this impedance, if this voltage is constant, this impedance you consider the resistor, right? You match the two resistor. Now, if you use AC voltage, there's real part, imaginary part, then when this you want to maximize, you have self-conjugate, right? We highlight again and again, have self-conjugate, okay. So, and now, how you are going to use control to achieve ideal input impedance? Here, I want to highlight one case. Okay, very simple understanding. Okay, now so this is okay. You measure the generator's velocity, right? Omega, right? You want to control the torque or control the current, right? You design the controller ZC, and here we take ZC as PID controller. This is P gain and integration gain and time velocity, right? And velocity time P is more like stiffness effect, and velocity time here and velocity integrate. Let me say that what I said is wrong. Okay, and velocity time Kp, what's that? Damping, right? Velocity time a constant, generate force, that's the damping. Okay, and velocity time 1 gain divided by j omega, what's that? J omega you can consider 1 over s. 1 over s means integration. Integration, velocity integration will be displacement. So this is damping term, this is stiffness term. Okay, I say again. Okay, so that is torque, that is velocity, right? And velocity time again corresponding to damping, right? So you have velocity divided by s, 1 over j omega, the displacement. Displacement time again, that is stiffness. So Kp corresponding damping, Ki corresponding spring. Okay, let us say you design very simple PI control with velocity feedback. You control the torque or control the torque current. The system is like that. This two-terminal system, right? The terminal corresponding to here and combined the torque, right? And then you have the velocity. Let me see, I hope. Okay, and you have velocity here. You measure velocity, you give the velocity generated. Now that you measure speed, right? And the generate torque, right? And then the torque and the input torque add together. That's totally the torque to the PTO system, right? PTO system here, the first item, that is ZD already here, right? And for example here, voltage and current relationship, you have ZW, right? And from the torque to voltage is coupling through here, right? This is, okay, this is break time. Okay, so give me quick moment. Okay, so anyway, so what I mean, you give velocity, right? And you control the torque, right? And you want to achieve the closed loop voltage current relationship. The closed loop voltage current relationship is impedance ZL, right? Now you write based on this, you write a closed loop. Basically, you control the motor, right? Measure speed, control the torque or current, achieve ideal the electric impedance. So that is to show how the impedance is controlled with motor torque control. So all this is function of every element, right? This is motor's impedance, right? That part ZD, that is transmission impedance, right? So you control the torque, and with velocity feedback, you get an idea impedance here, right? So now this is mechanical energy and electricity. Let us say this is mechanical energy, this is electrical energy. Let us take break. After break, and we can continue. Okay, yeah. Okay, thank you. I need to teach you a little bit faster. Problem is hard. I didn't realize you guys didn't learn control. It's fine. Don't get scared. You now know Fourier transformation. You know Laplace. Then you can learn that. I'm going to finish the control code design part. Okay. Then after that, we are going to talk a little bit more beyond the engineering control code design. So it's just now in the break I chat, most students in ocean engineering and you didn't learn control. It's fine. And in my undergraduate study, I didn't learn control either. Later, I learned the control in graduate school and also read some book myself. Okay. So control code design, as you can see, it is a nice framework that allow you to consider hydrodynamics part, mechanical transmission part, generator part, and the feedback control part, right? You put everything together. Now it's a nice framework. You can consider the mechanical power and electrical power. Mechanical power basically is torque and rotation speed. And in that part, you take that as output impedance. And the electrical part, right, you consider all the impedance lump up together, and you can maximize the power output. What I mean, electrical power output with considering feedback control. So, and I give you result about here, and more details you can find the paper. And basically, in this system, the flap system, we design the controller, right? And we can maximize the mechanical power output, and from here, torque and rotation speed. Or we can maximize the electrical power output, right? Voltage time current. And so far, we talk about, okay, put the PTO force and velocity in phase. Actually, the concept is mechanical power output. So, we design the control parameters and the PTOs in rotation inertia, PTO damping, PTOs stiffness, and controller KP, KI, KP corresponding damping, KI corresponding stiffness. Okay. So important conclusion I told you here, if you maximize the mechanical power input, mechanical power, in some case, your electric power can even get negative. The reason is, in some cases, in that case, a lot of energy get dissipated, right? The energy dissipated is more than that energy input to the system, right? Therefore, the best is to consider the performance index as electrical power output. So we also can do further optimization, in which we can consider the geometry design. For example, in this one, we consider flaps width and height in the system. And in this one, we take a two-loop design. The first loop we design the PTO's rotation inertia, PTO's damping, and electrical gear ratio, in coupling coefficients, consider coupling coefficients, consider the transmission ratio. Okay, outside loop we consider x dimension, y dimension. So, and this is so each one outside we more like separate into different case study and do the complicate two loop system to maximize the power output. Okay, and meanwhile reduce the load to the flap, the pressure per area. Okay, details is in this paper. Okay, so I stopped 1 or 2 minutes. I just want to get you guys think about control core design framework, right? Control core design, I normally say we put a control engineer or the chief engineer, you think about that. And it can be a little bit broader. Instead of control core design, we call engineering core design or certain level core design. Basically, you need to consider from the structure side, shape, right, geometry, to the PTO design, right, rotation inertia, ball screw transmission, or the type of system, or rack pinion, whatever like that. And we also need to consider how to control the system. It can be very simple PID control, and it can be model predictive control, right? No matter what, we need to consider all the engineering system together, including structure side, including PTO side, including control side, right? You put it in one nice framework, right? So this is engineering system core design. And you get a sense, wow, wave energy, very complicated system. Vibration, right? Fluid, control, power electronics, right? Dynamics, design, right? It's complicated. As I said, this area is large. You jump into this area, you extend your knowledge by learning from others, right? So don't think I have to know everything. You don't need to know everything. You jump into this area, you stay in one side, you extend your knowledge. Okay. So, however, you fear, I can tell you, okay, I can tell you this is engineering certain level core design. The concept is not enough. You say, wow, I need so many different disciplinary knowledge. Professor told me, wow, it's not enough. What do you mean? So here, this is next 1 hour, I will tell you why it's not enough.